We're going to start at page 20, and we are going to kind of jump around in the notes because I've found that I kind of want to simplify it and make sure you've got the first part solid before I go and do a full hypothesis test, which is what we're going to be talking about today. So we just finished chapter 19, and so what was it that an interval did for us? What does a confidence interval tell you? What information does it give you? Okay, good. So it's kind of like this range of numbers that you're hoping your true proportion or your true mean or whatever it is you're estimating is in. Okay, so you're hoping you kind of have an estimate for that true population value. Good. So that is true. That is what your confidence interval is doing. Now, a hypothesis test is the next thing that we're going to cover. Anytime there's an experiment or a study done, all the medical journals are just all about hypothesis tests. They did a test on this drug. They did a study on this. So they got these particular numbers, and that's what we're going to be talking about is how the format of what a statistical test actually does for you. And we will find that the goal is to be able to have an answer as to if the claim that whoever it is that's claiming something is or is not true. Okay, so in a sense, we're seeing if we have evidence to say, okay, I don't have evidence to say you're wrong, or if we have or not. So do we have evidence to say your claim is wrong or not? Like our blue M&Ms. Did we have evidence to dispute their claim of 20% blue M&Ms coming off the assembly line? Okay, so the first thing that we're going to do is we're going to get a good idea, and we're going to practice these things called a null hypothesis statement and an alternative hypothesis statement. So that's the first thing we want to get a solid understanding of before we go into running a full test. So therefore, I'm going to have you flip over to page 23. I used to have my students just start off, let's do a hypothesis test, and I think it was just like, whoa, what is all this stuff? But I think let's get what a null and alternative hypothesis are first. Okay, so first, null hypothesis is represented H with a little o. Okay? And a null hypothesis is a statement of what is being claimed about the population. Okay, so the null hypothesis is telling us what is being claimed about the population. And then we're going to collect evidence and see if we have evidence to reject that claim or not. Okay? Now, the alternative is represented H with a little a. Okay, and so the H, the alternative, is a statement that we are wondering about as to if we have evidence to dispute the null hypothesis. So our alternative is wondering about the evidence and seeing if we have evidence to dispute the null hypothesis. Now, there are three different ways, typical signs, or number values that we deal with when we're wondering about disputing the null hypothesis. One is we wonder if the number that they gave us, the parameter that their claim is really less, should be really less than what they claim. Okay? All right, so our alternative could be about, we think the value is less than what you say. Or maybe you think it is greater than what they say. So less than or greater than. Sometimes they don't tell you a direction. Sometimes you will be just disputing that somebody gets the same value as somebody else, or that it is the same as it, or that there is precision. You don't know, yes, less than or greater than, so you just say not equal to. Okay, so those are the three signs that we'll be using whenever we do an alternative hypothesis. And so let's go ahead and just practice some of those. And so we're going to jump down here to your notes past some of this information, which I may get to later, and let's practice. The first thing that we're going to do is write a parameter of the parameter of interest. Okay, so when we did a song the other day, let's see, oh, I know, the confidence level, okay, it was about if it contained the parameter of interest. And so I kind of stopped the song there and I said, okay, let's talk about what parameter of interest is. So what is a parameter? What does that word parameter have to do with? Any ideas? So we want to know that. A parameter is something about the population. Okay? So we were wondering on our intervals if we captured the true parameter that we were interested in looking for. So a parameter is the population information. And the parameter of interest means that population item that we're interested in, like the true proportion of water on the globe or whatever. So that's what we want to first write. So on this first problem here, a car dealer advertises that its new subcompact model gets 47 miles per gallon. You assume the dealer would not underrate the car, but you are suspicious about the claim. So you are wondering if he's, is he just kind of exaggerating how well the miles per gallon are. So first question I have, is this a proportion problem or a mean problem? It is mean, because miles per gallon is a numerical value, so that's a quantity, so average. So this is a mean problem. Okay, now, what are we trying to make a statement about? This will be about the average what? Miles per gallon of this vehicle. Good. So the way we define our parameter is this way. We write the population value of mu equals, and the first word I'm going to use is average, because mu is representing the average miles per gallon of all this type of cars. This is a claim about the population. Okay? And so then next, the way we write this is the null hypothesis will be written this way. We will write H with the little o, okay, H with the little o, and then a colon. And then we write, okay, so that's their claim. So they are claiming that the mu is 47 miles per gallon, okay? So that's what their claim is. Now, we are wondering about that claim. We're wondering if we have evidence that that claim, that the real value, the real miles per gallon is actually what, are we wondering? If it's less than, right. So we're wondering, is the average miles per gallon actually less than 47 miles per gallon? Okay. Is the average less than 47 miles per gallon? Okay. Very good. So that's how we write the alternative. And then, eventually what we'll do, we'll go collect the data, see if it's unusual enough to allow us to reject the claim. Okay, that's where we're headed with this. All right, so let's take a look at the second one. A package delivery service claims that it takes an average of 24 hours to send a package from New York to San Francisco. An independent consumer agency, so maybe like Consumer Reports or something like that, is doing a study to test the truth of this claim. Since there have been several complaints about the company not meeting its delivery times. So is this a problem about average or proportions? What? Okay, it's the proportion of what? Ah, I see that. Let's see here. So we would say that if they told us the company claims that, they're saying that 100% of their packages get there on time. They're not talking about that that 100% of their packages get there on time. They're telling us, they're claiming that the average of all of the packages is 24 hours. So that's a little different, and I can see where you would want to maybe think proportion, but based on the information we have, they don't have a claimed percent that make it on time. They have a claimed average amount of time. So therefore, this is an average problem. And it's mu equals the average time it takes to send a package with this company from New York to San Francisco. So you want to give a full description. It's not the United States Post Office. It's not Federal Express or even UPS. It's whatever this company is, which may be one of those, I don't know. Okay, so now, what would our null hypothesis say? Okay, good. So our null hypothesis would say that the mean equals 24 hours. Now, sometimes I get people leaving off the mu here. So HO colon mu equals 24 hours. Okay, don't leave off that mu. And so then what would our alternative be about? Good. We have claims, or people are wondering if it's actually taking greater than an average of 24 hours for the package to get there. Okay? All right, so I'm going to give you a few moments, and I want you to try the number 3 and number 4 on the top of the next page by yourself. So take a few moments, try those, and then we'll check them. Let's check those. Okay, so what was the number 3, mean or proportion? Mean. And what was the mean about? Good. The average diameter of all such bearings. The null hypothesis is that mu equals 6 millimeters, but look at the alternative. It did not indicate we thought they were too small or we think it's too big. It just says we need it to be precise. So that is a not equal to. Yes? Yes. I wonder if this covers that, all such. But yeah, sure. I'm sure it would be better if I had put, from this company. From this company. Okay. So the question was, should I put from this company? And it's kind of questionable if all such takes care of it, but any more details you give is always good. Okay. Now, what did you think about number 4? What kind of problem was that? Good. See, that's what a proportion problem looks like. Now, let's be very careful. Let's look at what you said the parameter was. P equals, so make sure you're using P's, not mu's, because these are about proportions. And do you see my first word is P equals the proportion, okay, of all heart attack patients that die, present tense, not past. Even though it said died in the sample that they had from 2006, or the information they had from 2006, we are making a statement about the here and now, currently what's going on. So it's P equals the proportion of all heart attack patients that die for any reason in the first 30 days after hospitalization. The null is that P is the same as it was in 2006. So if there's been no improvement, if everything has stayed the same, it's still 0.161. I usually put decimals for write them there, and then in my conclusion statement when I do a test, I might put them in percents. Okay, and since we are wondering if it improved, what would an improvement in a death rate mean? You went which direction? Less, yeah. So that's why our alternative is P is less than, because the death rate improved, so there's less death. Okay, so that's all I was going to do with those. Now, I want you to go over to page 26 and 27. I'm going to give you 10 minutes to do that. If you hustle, you might get it all done and have no homework. But you're gonna do that, and then we'll come back together and start talking about a full hypothesis test. Okay, I'm gonna have you guys go back to page 20, and what I want to do now is run a full hypothesis test, show you what an entire hypothesis test includes, which will include teaching you a couple of things, namely what this thing called a p-value is, what alpha is, what values to reject the null. Anyway, so some and what statistically significant is. So there's some things here at the end I'm going to teach you. We'll go into those more in depth tomorrow. So I'm just going to kind of introduce to you some concepts today, and we'll do those songs. Now, just like when we did our intervals and there were things we had to include, and we followed the panic model. So we use that mnemonic device. We're going to use phantoms, and phantoms will help us include everything that we need to include. You actually just practiced the P and the H of the phantoms model. P stands for that parameter of interest that you're trying to define, defining the parameter, and H stands for the hypotheses statements. Okay, so you just practiced doing the P and the H. So A is the assumptions, which are your conditions. N will name what it is, and then we'll do some, then back here when we get to TOMS of the phantoms model, that's where it kind of gets a little different, all right? So let's take a look at this first problem, and we'll learn this through this first problem. So since we've seen this problem before, but we haven't run a full test on it. So problem number 1 says, census data for a certain county shows that 19% of the adult residences are Hispanic, so in the county. Suppose 72 people are called for jury duty and only 9 of them are Hispanic. Does this apparent underrepresentation of Hispanics call into question the fairness of the jury selection system? So, first, mean or proportion problem. Okay, proportion. All right. So it's a proportion problem. So I need to define what P equals. And so at this time, I want you to think about what you would say P represents. Okay, so P is what? What is P meaning in context? The what, Hispanics? The proportion of what? Okay, there has to be jury in there somewhere. Aha, okay. So, here's my question. Is this about the proportion of the Hispanics in the county that are called in for jury duty? Okay. Or is this about the proportion of those that are called in for jury duty that are Hispanic? Those are two different things because your denominator is different. This first one says, out of all the Hispanics in the county, what proportion of the Hispanics in the county are called in for jury duty? But this one is what this is saying. 72 people are called in for jury duty, and of those called in for jury duty, the certain proportion of them are Hispanic. Okay, so proportions, the only tricky thing about proportions is you really do need to think what your denominator is. What is it out of? Okay? All right, so let's define that. Let's go to so we have a phantoms model. You have an outline on this next page, and this is what we're going to be filling in. Okay? So this first one. So P equals, and since it's a P, we know our first word is going to be proportion of residences, or all such residences called for jury duty that are Hispanic. And there's some notes in there about what the P represents, okay? Always use a parameter, a p or a mu. Okay? Okay, now, hypotheses-wise, what would our null hypothesis be? That p equals 0.19. Good. Because if this is just a sampling variability issue, then it should be somewhere close to then our proportion should be somewhere close to 19%. Okay, what is the alternative that we're wondering about? Less than, because we are wondering if the Hispanics are being underrepresented, okay, in the process. Okay, very good. So next, the assumptions and conditions. These are all the same. And so I actually have the answer key done up of this that I'm just going to show it to you real quickly. But I want to do one thing. I want to mention a mistake that I made. I actually had to redo the answer key of this yesterday because I had made a note that last year I had done a wrong number. So let me point that out to you because it's an easy thing to do. So, of course, randomly selected county residences are called in for jury duty. That's assumed because it wasn't stated. And then our 72 is less than 10% of all such residences called in for jury duty. Okay, here is where I had made my mistake when I did my key in the past. I kind of did what I did for the interval. I just put, 9 is greater than, well, it wasn't greater than or equal to 10. You know, we had gotten 9 out of 72. This number here has to be your true p. That's the hypothesized p. Don't put p hat there. So we're back to having a hypothesized, a true p. It's hypothesized, but we still use it. So n p and n times the 1 minus p. Okay? So there's our large enough, so our normal model applies. Okay, no biggie there. Now, n stands for the name of what's going on. The name of what we did recently was a 1 proportion, what? Z interval, okay? This is going to be called a 1 proportion Z test because this is a hypothesis test. So we now have learned two kinds of things, a 1 proportion Z interval and a 1 proportion Z test. Okay, so with our test, our goal is to see if our sample gives us evidence to reject the claim. Okay, what kind of results do you think we're going to get? What kind of results do you think would give us evidence to reject the claim? What kind of sample would give us evidence to reject the claim? And say, hey, claim, I don't think you're true. Ideas? Thank you. Yes. Outliers. If you're going to be getting a sample that's an outlier sample, then that's going to be unusual, okay? And it'll give you evidence to reject the claim. Very good. So our next thing is to get the test statistic, which for us are z-scores, okay? So I just kind of wrote, here's some information that I wrote here. Let's take a look over here. So the mean of the p-hats is 0.19. Standard deviation of the p-hats, use that formula. Square root of 0.19 times 0.81 over 72. Okay, this was the standard deviation of the p-hats, and that's 0.046. Okay, which, by the way, the sample results that they got, the p-hat that they got was 9 out of 72. And that's 0.125. So they're wondering, is that just because of sampling variability, or is that significantly low? Okay. So our z-score is your p-hat minus your p over your standard deviation of p-hats. And that's your negative 1.41. So if we were to just consider that z-score, do we have evidence to reject the claim? No. Why not? Because was our sample unusual? Our sample was not unusual. Our sample could just have happened because of sampling variability. So let's now have some discussion. Okay, so let's see here. Let's add a page. So here we go. Here is the claim. The claim is the null hypothesis that the center is at point 19. So we're going to take a whole bunch of samples. And why do I have these everywhere? Why are these all in different places? Very good. When I used to ask you that question, it'd be like cricket, cricket, cricket. But now y'all know this is because of sampling variability, because you got something different than me. But if it's not too far away, then I'm not too worried about it. Okay. Here's the thing, and here's where the new stuff that you learn comes into play today. Hypothesis tests actually cannot be quote unquote proven or not. You cannot reject or fail to reject based off of the z-score. Okay? Now we've discussed whether things are unusual or not, but in real statistics, you cannot decide to reject the claim or not reject it based off of a z-score. So what you have to be able to mathematically decide if this is unusual or not, if the claim should be rejected or not, is what's called a p-value. And we'll define this tomorrow. So y'all don't need to write this stuff down. Just kind of follow along, and we'll write it all out tomorrow. So p-value is the reason that I started doing our songs, because this is probably the most misunderstood definition. So it was the very first one. P-value is the probability of getting a particular sample. So let's say our sample was right here. Okay, here's our sample. P-value is the probability of getting this sample or something more extreme. So see, here's the probability. And more extreme goes down in this case. If it was an upper sample and I was wondering about going higher than, then I would go up. My more extreme would be up. But a p-value is the probability of getting this sample or something more extreme if indeed the data is around this null hypothesis. If the data is centered around the null hypothesis, then the probability of getting this sample or something more extreme is the p-value. Okay, so that's the definition of that, which brings us to our first song. Okay, so let's see here. Definition of p-value. I heard this the other day and kind of was weird to sing the real words to it. I couldn't do it. Do you remember when we used to sing the p-value is the probability of getting this sample or something more extreme if the null is true? Okay, so now some visual to go with that. Here we go. The p-value is this probability right here, this red area. This sample or something more extreme if the data is centered where the null hypothesis is. Okay? Now you're going to get to sing that one while I demonstrate with our this thing here. Okay, because this is so important. You got to know this. Here we go. We're not doing that song anymore, so let's rewind. Here we go. Do you remember when? Here we go, you gotta sing. We used to sing, the p-value is the probability. Okay, here it is. Or getting this sample or something more extreme if the null is true. My coloring didn't work on that. This sample or something more extreme. The p-value is the probability of getting this sample or something more extreme if the null is true. So if the data is truly centered right there, then that's the probability that we just figured out. Okay. All right, so that was the first concept today, that it's important to understand what this thing called p-value is. All right, so next, let's talk about, okay, so what? You get a p-value. You run a test, you get a p-value. What's that going to do for you? How do you know if you reject or you fail to reject? Okay, so next, there is this thing called alpha, and it is typically told to you. Like somebody says, use an alpha of 0.01 or use an alpha of 0.05. The default, if somebody doesn't tell you, is 0.05. Okay? It is the size of the rejection region. And we'll write this down tomorrow, so don't worry about that. So it is the size of the rejection region. So I want to give you a picture here. So here, let's say this right here, this black line represents my alpha, and this black shaded section is 5%. Okay, I'm going to say alpha is 5%. All right, so I want you to compare my red shaded area to this black shaded area. If my sample is here, this p-value is the red shaded area. If my red shaded area is the probability of getting this sample or something more extreme, if the null is true, okay, so here's my p-value, and then look at the alpha. It's that black area. Which one's bigger? Which one has more area? The red or the black? No, the red. Do you see there's more red than black? Black is this big. Red. Okay. Oh, okay. Yeah. So the red is the whole, this whole amount from infinity to here. Okay. So the whole thing is red, and then that little part is black. So you agree red is bigger? Okay. So in this case, this is a picture of the p-value is greater than alpha. Okay. The p-value is greater than alpha. Now, question, is my sample in the rejection region? Is this right here, my p-hat, in the rejection region? It is not. So if my p-value is greater than alpha, then my sample is not in the rejection region. Okay, let's go the other way. Let's suppose I have this little purple sample here, p-hat. Here's my purple sample, p-hat. And here is the probability of finding this sample or something more extreme if the null is true. So here is my p-value for purple. Compare the size of that p-value to the black. Which one is smaller? Purple is smaller than black. So here p-value is less than alpha. Okay, so p-value is less than alpha. Where is that sample located? It is in the what? Rejection region. So the moral to that story is, if your p-value is less than alpha, it is happening because your sample is in the rejection region. So what I'm leading you to the next song is, if the p-value is lower than alpha, then you are now in the rejection region, of which you would then reject the null hypothesis. So you can see from here that if the p-value is low, we will reject HO. Okay? So if the p-value is low, as demonstrated here, see, if this is a smaller p-value than alpha, then we will reject HO. And that it means the null hypothesis has to go. Okay? Now I say reject if the p-value is low. Reject HO. But I'm not going to lie to you that some people like to say, if the p-value is low, reject that ho. Okay? Now, mathematically, we don't like to say ho for, I guess, obvious reasons, but HO. So we'll just let you decide how you would like to sing this song. So here we go. If the p-value is low, reject HO. U is low, reject H. The null hypothesis has to go. If the p-value is low, the p-value is low, the null hypothesis has to go. See, look, that hoe got to go. Okay? All right. Okay, so that's the end of that little topic. If I can stop this song here. No, don't sing this one. I can't stop it. It won't stop. Stop. So earlier today I tried to stop it, and then like more versions of it kept popping up. So it was like a round on top of it. It's like more on top of each other, more on top of each other. Oh my gosh. Okay, I tell you what. Here we go. We'll just use it. Sampling variability is happening because over here, just sampling variability. You got different data than me. But look, if my p hat is in the rejection region, then that is called statistically significant. Okay? Let's see if it'll stop now. Okay, there it goes. And there's the next song, which it won't let me stop. This is just going to go on all day. Okay, so you know what? We are just about out of time. But let me talk to you real quick. Again, one last phrase was that statistically significant, and we'll listen to that tomorrow. But if you get this this sample in the rejection region, it is called statistically significant. Okay, that means you rejected the null. Yes. Absolutely. You could have the rejection, you could have the flip-flop of this, and the rejection region could be in the upper side, okay? So there's a couple of ideas. We'll finish that test tomorrow, we'll finish that information tomorrow and kind of review these as well as do statistically significant. But if you finished your page 26 and 27, you're good to go and you're done. Okay, what? Yes, there can. There can be two. That's if you have a not equal to test. And we'll talk about that also. So